Thanks everyone for joining us. We're super lucky today to have Dr. Amanda Lyons here from Pacific Northwest National Lab. We were just discussing this, she got her undergraduate degrees in Purdue University, then went out to Washington State for a degree in a PhD in analytical chemistry. We were excited to invite her here for a number of reasons. She does work related to process control and sensors for nuclear materials processing. That's relevant to the Enabling Technology and Innovation Consortium that we're part of, and NNSA funded, and so we sort of crossed paths in that program, but also a lot of relevant work to the molten salt analysis and work that goes on in our research labs here at UW. And so there are a lot of different people that were interested to hear what Dr. Lyons had to say. And so we thought it'd be great if we could have her come and give a seminar. So with that, I'll hand it over and welcome.
Well, thank you for the introduction, and I'm excited to be here, and hopefully folks can see my screen now. So I will be talking about some of the work that I and my team are doing out at Pacific Northwest National Laboratory, or PNNL. But before I dig into the real technical meat, it might be valuable just to give a little bit of a background about PNNL and the National Lab system. So PNNL is one of 17 national laboratories across the United States, and they tend to have certain commonalities. Really, we tend to look at very big problems or be mission driven. We tend to focus on high risk, high reward, long-term work, but really, and perhaps the most exciting commonality from my perspective is the fact that we have the resources to make some very exciting capabilities or state-of-the-art facilities that let us tackle some of the biggest challenges facing our nation. Now, PNNL is actually located right out here in Washington State, and we were just talking about this before the recording began. That's actually desert. Most people think Seattle, wet, rainy when they think Washington, but PNNL is on the eastern side of the state, right by the Columbia River, so still lots of fun water sports. But you can see a picture of the campus here, or at least a big chunk of it. I actually work a little bit north of where this picture was taken, out in the radiochemical processing laboratory. That's a Category 2 non-reactor nuclear facility, which essentially means that we can work with a lot of material and do some very exciting and important work out there. Now, this campus is pretty large. We've got a lot of different staff members. You can see over 4,000 listed on this slide. And we do a lot of work in a lot of different areas. We actually break ourselves up into different directorates to kind of help group ourselves. One directorate is the Energy and Environment Directorate. That's where I do a big majority of my work. So you can imagine this directorate is focused on things like energy infrastructure, renewable energy, nuclear energy, and so on. But we do have other directorates, an important example being the National Security Directorate, which is another area where I do some of my work. And here we focus on things like non-proliferation, cyber situational awareness, and so on. Ultimately, there is a lot of diverse and exciting work that we do out at PNNL, and if this sounds interesting or exciting to any of you, I'd highly recommend you go and check out this website right here, just to see what kind of opportunities there might be for you. And if you are a student who's looking for an internship opportunity, hold that thought, because I'll be digging into that a little bit more towards the end of my talk here. So with that introductory material out of the way, I think we can start digging into the technical aspects of this. And to set the stage, first off, a lot of the work I'm talking about today is going to be focused on what we're doing in the nuclear energy sector. And this is an incredibly important area because nuclear energy is a key component of a diverse and green energy portfolio. In fact, I think most people here are aware that with some of the very aggressive deep decarbonization goals that we're setting for ourselves in this country and internationally, we have some challenges to meet. In fact, there are a lot of models out there that indicate nuclear has to be a part of our solution in order to meet many of those goals. So my team's goal is to help nuclear overcome some of its initial challenges, really take it into the future and get it out there deployed and meeting our energy needs. Meeting our energy needs. And I want to point out that nuclear energy is a pretty wide field. Most people, when they think nuclear energy, they think reactor operation. That's the business end. That's where you get all the energy that goes out and does work. But it's important to keep in mind that there's a lot more to nuclear energy. You know, before you can turn that reactor on, you have to produce fuel to go into it. And after that fuel is done in the reactor, you've got to do something with it. Recycling is a very sustainable option, but ultimately, at the end of life of all of these materials, you have to be thinking about processing that waste. Now, my team has the very lofty goal of building tools that can help us throughout the entirety of the nuclear fuel cycle here. And that can seem like a bit of a stretch, but if you dig into everything from fuel production to waste processing, you see that there's some big commonalities. Specifically, through all of these stages of the nuclear fuel cycle, you're looking at a lot of chemical processing. And if you want to make chemical processing safer, more efficient, more cost-effective, you need to be thinking online monitoring. Online monitoring is all about getting a sensor or a probe into a process so that you can understand in situ and in real time what's going on in that process. This provides really valuable information for a wide variety of needs, everything from fundamental characterization to deployment. So, as an example, if we're thinking about characterizing the fundamental chemical behavior of a system, getting probes into our samples to see what that system is doing without disturbing it is a good way of really understanding the true nature of the system. Alternatively, if you think about designing, say, a new recycling scheme for used nuclear fuel, if you can get online monitoring probes into that process, you can more efficiently understand what's going on in that process and ultimately more efficiently design and optimize that process. And of course, if you're thinking about taking any of these systems and deploying them out into industry, in any industrial scene, if you have probes in your process, that lets your operators better understand and control the process as it's occurring. Again, reducing costs, improving product quality, and so on. So a ton of really valuable applications. But it's important to recognize that online monitoring is a very diverse field. There are a lot of different tools out there that are geared towards answering different questions about a process. I and my team are particularly interested in answering questions related to the chemical composition of a process. So for example, in this process stream, is uranium present? How much uranium is there? What oxidation state is it in? What speciation is it exhibiting? Is it playing around in the pool the way you would hope it is? And if we want to answer those types of chemical composition questions, really one of the best tools we have available to us is optical spectroscopy. That's all about getting light into your process stream or sample, looking at how light interacts with the material, and then gleaning that process information from that optical data. Now, we like optical spectroscopy for a lot of reasons, not only because it can give us a ton of detailed chemical information, but because it lends itself very well to online monitoring applications. You know, if we're thinking about getting our probes into these various nuclear material processing, we need probes that can stand up to it. They need to be fast, robust, and versatile. And I want to dig into this idea of versatility in particular, because that's really important for us. Again, earlier I mentioned our goal is to build tools that can be used throughout the entire nuclear fuel cycle. So that means we're looking at a lot of different process types, a lot of different schemes or conditions. So we need something that we can flexibly take into a lot of different process conditions to give us different types of information. And again, optical spectroscopy is ideal for this. You can take optical probes and optimize them to look at different system matrices. So we've built tools to look at solids, liquids, gases, even molten salts. And you also need to be able to take these optical probes into different sizes of processes. So for example, we've taken probes and we've applied them to microscale systems, so microliters per minute, but we've also applied them to commercial scale systems where you're talking hundreds of gallons an hour. So again, a lot of flexibility in terms of where we can engineer these probes into. But perhaps the most important level of versatility of optical spectroscopy is the fact that we can get just a ton of different types of chemical data from different types of optical approaches. So for example, Raman spectroscopy as a singular approach right here is a vibrational form of spectroscopy. So we can use it to go after polyatomic species. So we could use a Raman probe to look at everything from actinide oxide ions, organic species, inorganic oxoanions, and so on. Now, if we want to probe the system differently, go after different kinds of species, we could use something like UV-Vis near-IR absorption. That's electronic, so again, just looks at it a bit differently. So we can get things like actinides and lanthanides in multiple oxidation states, different metal ligand complexes. And if we can't get the chemical species that we need with something like Raman or UV-Vis near-IR, we have a lot of other techniques that we can take and utilize. That includes FTIR, light scatter, optical density, fluorescence. The list is quite extensive. And even beyond that, if we're looking for comprehensive understanding, we're not limited to using just one form of optical spectroscopy. We can actually combine techniques into a single sensor, so say Raman and UV-Vis near-IR, so we can get a comprehensive understanding of the system. So a ton of flexibility in terms of what chemical species we can go after. Now, I've been talking about how great optical spectroscopy is at getting us the data we need, but we do need to be realistic. So we've got to take a step back and recognize that this greatest strength, if we're looking at the title of this slide, is a double-edged sword. It's also the greatest weakness of optical spectroscopy, because you can imagine that as you start looking at chemical systems where you have multiple chemical species that are optically active, you're going to start getting an overlap of the different fingerprints of the species you're after. And it can be quite challenging to isolate the information you do care about from the information that's otherwise obstructing your analysis. So ultimately, optical spectroscopy does have some weaknesses that we have to overcome. There's actually two big ones that we tend to think about. The first is chemical complexity, like we were just discussing, and the other is getting into harsh or challenging environments. So think highly turbid streams or molten salt systems. Now, for this talk, I'm probably not going to have enough time to dig into the harsh or challenging environments in a ton of detail, but I do want to note that this is an important and exciting aspect of the work that we do. And if there are questions afterwards, or if folks want to reach out and learn more about this, you are perfectly welcome to. Instead, we're going to focus a little bit more on that idea of chemical complexity and how we can take that highly complex data stream with a lot of those overlapping or interfering fingerprints and transform that into reliable and accurate information. And there's actually a couple of ways to do this. Ultimately, if you're looking at complex chemical data, the answer to getting good data or good information out of the system is to enhance your selectivity. So improve your ability to isolate the information you're after. There are a number of ways to do this, or skin this cat, if you will. And I'm going to talk today about two of our favorite methods for enhancing selectivity for the targets that you're after from the complex data stream. I'm going to talk about chemometric modeling and electrochemistry, and how we can pair those with optical spectroscopy-based sensors to get the information we need. So let's start off with that chemometric modeling. This is a form of machine learning. Essentially, it's a tool that lets us take an advanced approach, a multivariate approach, to looking at data streams to pull out the information we're after. And I always like to start off explaining chemometric analysis by comparing it to more traditional data analysis approaches. So something like single variate analysis, where you're looking at just one point of an optical data set. So let's go through a quick example here. I like graphical examples. And what we're looking at here are a series of visible absorbance spectra of a fairly simple chemical system. It's nothing but nitric acid held constant at 1 molar, and plutonium-4 varied from 0 millimolar up to 30 millimolar. Now this data is absolutely beautiful. You get that really nice plutonium-4 fingerprint. You see that it changes with concentration, increasing in a linear fashion, and it's nice and reproducible. So in this system, you can use single variate analysis. You can pick your favorite wavelength, and then you can plot the absorbance at that singular wavelength as a function of plutonium-4 concentration. And essentially what you get is a relationship relating those two. It's Beer's law. I'm sure most folks have hopefully remember this from Gen Chem, but essentially what this is a tool that can relate a regression coefficient between your absorbance response and your known concentration. And this is a tool that forever in the future, if you encounter plutonium-4 under these conditions, you can go back and use your Beer's law equation to calculate the concentration of plutonium based on your absorbance spectra. Now, unfortunately, it's very rare that we get data that looks this nice in a real complex or industrial chemical process. We tend to see data that has a little bit more going on. Now, this spectral example right here starts showing some of that complexity we might anticipate in a real chemical process. This is still a very simple chemical system, just like the previous slide, nothing but nitric acid and plutonium-4 in here. But in this case, we're holding plutonium-4 constant at 15 millimolar, while we vary the nitric acid from 0.5 molar up to 10 molar. And you can see with that change in matrix, your plutonium-4 fingerprint changes drastically. So looking at this data, you have to ask yourself some questions. First and foremost, if I want to quantify my plutonium-4 in here based on the absorbance spectra I measure, well, what wavelength do I choose? Do I have to run a pH measurement prior to running any quantification so I can make sure I trust my analysis value? Or what happens if I have new interference grow in, or if something happens to the baseline? Ultimately, we're asking ourselves, how do we find a meaningful regression coefficient to relate your plutonium-4 spectra back to a plutonium-4 concentration? And so that's where chemometric analysis comes in, this multivariate approach. Instead of limiting ourselves to a single wavelength, we're going to utilize the entire spectrum and look at that whole fingerprint to quantify our target. So let's go through a graphical example of how this looks. There's unfortunately never enough time to go through the math, but I have backup slides if people are curious. What we're going to do is we're going to go back to this spectra of showing this complex plutonium-4 behavior. We're going to zoom in on the primary response band for plutonium-4. And if we focus in on that over here in the top right, we see that that primary response band, as we go from low to high acid, drops, scoots over, and grows back in. Now, if we take this data and we use it to build a chemometric model, what that model is going to do is it's going to pull out principal components that essentially say which parts of the spectra are important for identifying and quantifying your target of interest. And it takes those principal components and it assigns them loadings. Essentially, you can think of a loading as something as in response at this particular wavelength is important to quantification of your target. This big mouthful. Let's go to a graphical example right here, where we're actually looking at the principal components that our chemometric model pulled out from this data. And we're looking at the loadings of those principal components. You can see we've got 4 right here. And essentially, a loading of 0 means response at a particular wavelength, not important. A loading with magnitude is very important. So if we focus out on this region of response out past about 520 nanometers here, we see that that's essentially a flat line if we're just looking at the spectra. We would not use that part of the spectrum to quantify or identify the plutonium-4. If we look at how our model looks at that same region, we see that our model essentially assigns that region loadings of 0. It agrees with us. That area is not important for quantifying your plutonium-4. However, this region right here, where we get a lot of this optical variability, we see that our model is working extremely hard to capture those different changing fingerprints. And this is actually quite fun. If you take a closer look at these principal components that our model pulled out, you actually see that they align with the fingerprints of different plutonium species. So if we back up just a moment here, this change in your spectral signature comes from a known phenomenon. As you increase your nitric acid concentration, you're going to push your plutonium-4 speciation from a mononitrado species to a di, to a tetra, to a hexanitrado species, all of which have their own unique fingerprints, and all of which line up with the principal components that our model was able to pull out. So ultimately what this means is that your model is indirectly pulling out this chemical information and using that to identify and quantify your species of interest. And so there's a lot of fun stuff we can do with that. We can dig into plutonium-4 speciation as we did just here, or we could go do something cool, like start thinking about how we could look at different acid buffer systems and try to characterize concentrations or pH of the analytes in there. So I want to show you a quick example here of a paper we recently published where we wanted to utilize chemometric modeling and optical spectroscopy in a slightly new and different way. Essentially, we wanted to rely on this ability of chemometric modeling to pull out that chemical information to help us characterize different aspects of the system. And I want to highlight really quickly, because this is a university talk, our first author here is actually one of the students on our team. We have a ton of students. You'll probably see a couple more of their names popping up through the rest of the slides. But what we did here is we wanted to reimagine how you could measure pH in a complex chemical system. If you think about an industrial process and you think about your standard methods of measuring pH with those nice little pH probes, those tend to be very fragile. They tend to require a lot of recalibration. They're not ideal for industrial application. We need something that's more robust. And so we said Raman probes, those are very robust. They can get us a lot of information about a system. And so we did a demonstration using Raman spectroscopy paired with chemometric analysis to follow the pH of a phosphoric acid system. And so just to dig into this data here, essentially what we did is what I was describing a moment ago. We captured a ton of optical data. We used that to build a chemometric model that related these different fingerprints to concentrations of our different acid species in here. You can see we go from the fully protonated and we slowly lose protons until we all go all the way to the fully deprotonated system down here. And we built models that let us relate that optical fingerprint back to the pH of the system. And we compared this to his calculations and pH probe measurements. And ultimately we were able to come up with a very accurate tool that could follow pH under these conditions. We've also taken this a step further with a paper that I think it recently was just accepted, also led by more of our students. Andrew Clifford, another undergraduate on our team, actually was the first author on this one, where we expanded that to start digging into, in more depth, concentration of these different species, accounting for things like ionic strength and activity coefficients. So there's just a lot that we can pull in to get detailed chemical information from a fundamental standpoint using optical spectroscopy and chemometric modeling. Of course, we can take this in a much more applied direction as well. And so just to give you an example of how we can employ optical spectroscopy and chemometric analysis for something that's more like operator process control, I've got this example for you right here. The CoDCon demonstration is a demonstration of doing a used nuclear fuel recycle, where the idea is we use a bank of centrifugal contactors to run countercurrent streams of aqueous and organic systems, ultimately taking a used fuel simulant and extracting out the parts that we want to recycle, so the uranium, plutonium. I don't have time necessarily today to go into the chemical details or process details of how this works, but if there's questions, I'd like to draw your attention to this reference right here. Instead, I want to point out the role that online monitoring played in here, because ultimately our goal with this process was to be able to control our product quality in real time. And anytime you're talking about real-time control, online monitoring has to be a part of your plan there. And this was quite fun. So we actually put sensors on all the inlets, on all the outlets to follow our targets in this process. But again, we're looking at a used fuel simulant. So I want to emphasize to you the complexity of this system. There were a ton of different target analytes that we wanted to go after. That included plutonium, uranium, and neptunium in a variety of oxidation states, as well as things like nitric acid. And of course, we had a bunch of other stuff in there as well. But to do that, we actually had to utilize sensor fusion. So we had to design our sensors to incorporate multiple forms of optical spectroscopy simultaneously to go after different species. So our sensors utilized UV-vis absorbance to go after, plutonium-3, 4, and 6, as well as uranium-4. We used near-AR to go after neptunium-4, 5, and 6, and we used Raman to go after uranium-6 or uranyl, as well as nitric acid concentration. And of course, in several of our process inlets or outlets, we had a whole variety of other fission products that you would anticipate in real used nuclear fuel. So ultimately, we're talking about extremely complex spectra that we could anticipate throughout our various systems. And I'm flashing up examples of UV-vis of different process inlets and outlets. And again, we don't have time to go into all of those. So instead, I want to focus on an example that was most important to this process. So the product stream. And in our product stream, we had uranium and plutonium, different oxidation states, and we wanted to be able to, again, quantify these species in real time so that our operator could control the product composition. And here's just a picture of the spectra right here. You can see fairly high optical complexity. You know, you don't want to just stare at this for hours and try to figure out what your concentrations are and try to use that to control your product quality with any real precision. So instead, we used our chemometric models. We collected the data, applied these models in real time, and output information about the system. And you can see a screenshot here of what that process was looking like. And this is just showing some of the data that was coming out in real time. In the background, you can see the system following the uranium-4 concentration as a function of time. Foreground, you can see some plots indicating the ratio of uranium and plutonium real time. And of course, we were quantifying a ton of other species not shown on this stream. To show you how important or impactful online monitoring was in this application, we've taken this data and replotted it after the fact. So what we're looking at here is for our product stream, the percent composition as a function of runtime. And I should point out that for this particular demonstration, our goal was to control the composition of our product stream. We wanted to be continuously producing a stream that was 70% uranium, indicated by the blue horizontal dashed line, and 30% plutonium, indicated by the red horizontal dashed line. So with those goals in mind, we had our online monitoring going. We started our process, and you can see our real-time output from our online monitoring in blue for uranium and red for plutonium, solid lines. And you can see after we started the process and it came to equilibrium, we were outside of that 70-30 goal. So our operator, based on this information from the online monitoring system, made a process adjustment, indicated by the vertical dashed black line. In fact, the operator made several process adjustments based on the online monitoring output until finally, between online monitoring and operator, we were able to get the system into that 30-70 target and hold it consistently for the remainder of the run. So very exciting news. Online monitoring enabled a form of immediate process control that would have been unachievable otherwise. I do want to point out there's a couple of other exciting pieces of this plot, and those are the circles, triangles, and squares. Those represent grab samples, samples that we collected from the product stream and sent offline for more traditional analysis. And there's two key things about those. First off, those markers line up very nicely with our online monitoring results, indicating that our output was very accurate. The other exciting thing is those grab sample details took anywhere from a day to months to come back to us, whereas the online monitoring was coming out every 30 seconds. So every 30 seconds, our system could tell the operator how much uranium, how much plutonium they had, and grab samples simply couldn't keep up with that. So we can see a tremendous step forward here in our ability to understand a process and control it in real time. And we actually ran several CoDCon demonstrations looking at different levels of used fuel simulant complexity and system conditions. And ultimately, we were able to see online monitoring did a lot more for us than just telling us product stream composition. It helped us do things like identify a failing pump, which would have been very difficult with just offline after the run analysis. And it helped us also do things like capture short-lived and entirely unexpected behavior from the system, things that are going to help us aim our more fundamental studies in the future to better understand how we can optimize or advance this process in the future. So CoDCon was a really great example of an applied system. We do have a number of other systems we look at that includes off-gas. And so here you can actually see some references and some work we're doing building online monitoring tools for molten salt reactor off-gas characterization. The idea being we need tools that will help us better understand what's coming out of the salt. That gives you some great insight into the chemistry of the salt, but also it's a tool that can help us design and operate in the future a off-gas treatment system, something that'll let us remove unwanted items from that gas stream and recycle it back into the molten salt process. So again, a lot of work we're doing there. And if we're thinking about molten salt, we can also think about some of the examples we've been doing with quantifying species in a molten salt system. I think this might be exciting to various members of the audience, where we've actually demonstrated several years ago that we could apply this online monitoring optical approach to molten salts and use chemometric analysis to quantify analytes in very complex salt compositions. So actually in this system, we were looking at, this was a lithium chloride, potassium chloride, eutectic, I do believe, and we were looking at salts that had up to 6 different lanthanides in them. And so you can actually see the different fingerprints of the lanthanides here. Again, if you look at all these lanthanides, you see a lot of that fingerprint overlap. So some pretty significant data complexity. Well, what we did in this case is we built chemometric models from pure analyte data. So you can see here an example of neodymium in the salt melt at a series of concentrations. We used those to build chemometric models for all 6 of these different lanthanides within that molten fluoride system, and built very accurate chemometric models. You can actually see here a parity plot for our chemometric model for neodymium. Sorry, it's lacking the label there, where we're comparing what we measured chemometrically to what we knew that neodymium concentration to be within the salt environment. And what we're looking for in a parity plot is a one-to-one correlation between what we measured and what we knew. That's actually the black line on this plot. And you can see that our data falls very nicely on there. And just to highlight an exciting aspect of this, the blue crosses on this plot indicate our training set systems. So again, those were pure samples. So nothing but neodymium in the training set for neodymium. The red diamonds are our validation set. So spectra that the model has never seen before, and it's trying to characterize neodymium in those unknown spectra. The exciting thing here is that all of those validation samples contained up to 6 of the lanthanides simultaneously. So extremely complex data, a lot of that spectral overlap, but we're still able to very accurately quantify neodymium and all the other lanthanides in that system as well. Now, while on the topic of molten salts, I want to point out that there's a lot of other fun stuff we can do in these systems. It comes down to the next topic that we want to dig into for enhancing selectivity, which is electrochemistry. So integrating electrochemistry and optical spectroscopy together in spectroelectrochemistry. Now, this is a very fun way of building sensors that can give you a different type of selectivity. Specifically, we can play around with I call it a light switch effect. If you think about something like plutonium, for example, and you think about plutonium in 2 different oxidation states, plutonium-4 shown in purple and plutonium-3 shown in green. You can imagine an electrochemically active species like plutonium. If we use electrochemistry to force plutonium to go from one oxidation state to the other, we're going to get it to switch between those 2 optical fingerprints, much like a light switch. And that's incredibly valuable if you're trying to isolate wanted plutonium signature from a bunch of other noise in the system. As a quick example of how that works, I've got here an example taken from the Heinemann group, where they were actually looking at a sensor system for ruthenium and iron, rutrispivy and iron trispivy actually. And their absorbance system was really limited to monitoring absorbance at 520 nanometers. And so in their sensor, they loaded their sample into their sensor. They're following 520 nanometers, which is great. They see an increase when they load their sample in. The trick here is that their sample contained both ruthenium and iron. And unfortunately, both ruthenium and iron absorb at 520 nanometers. So this is where they utilized that light switch capability of spectroelectrochemistry to isolate the fingerprints of the 2 species. So if you look at the electrochemical behavior of iron and ruthenium, you see these CVs right here, where you've got your iron couple down here at about 0.85 volts. You've got your ruthenium couple up here at about 1.1 volts. What this means is that if you go into the system and you apply potentials at different points, you'll get different oxidation states of your targets. So for example, if you apply a potential down here, let's say 0.75 volts, you've forced both species into the 2+ state. You come out here past that iron couple and apply a potential, let's say 0.95 volts. You're going to oxidize the iron up to iron 3, but that ruthenium is still going to be ruthenium 2. And of course, if you go all the way out here, apply a potential past the ruthenium couple, you'll have oxidized both species. Now, what's exciting here is that the 2+ species of both iron and ruthenium absorb at 520 nanometers, but the 3+ species does not. So that means they can use this couple, again, as a light switch. So they started off by playing around with just that iron couple, bouncing between oxidizing and reducing the iron, between your oxidized light off and reduced light on form. And then they took it out to play with the next couple, the ruthenium. And keep in mind, once they're playing with ruthenium, they've already turned off all of that iron signal. So they're able then to just play with the ruthenium only, turning ruthenium off by oxidizing and on by reducing. So in this way, they were able to isolate those overlapped fingerprints and determine how much signal was from iron and how much signal was from ruthenium. And so we actually take this into a lot of different areas to look at a lot of different chemical species. As a fun example, we've actually used it to look at different ruthenium systems. And I like talking about this example because it's a really valuable lesson for graduate students. This is actually some work that I did a long time ago. And we started off, we said, we want to build a spectroelectrochemical sensor that can work for hard to detect metal species. You know, we need something that's electrochemically active, optically active. If your species is not optically active, what do? Well, you can make it optically active. So if we take something like unbound ruthenium, let's say you've got ruthenium chloride of some sort running around, and you force it to bind with some sort of sensitizing ligand, let's say bipyridine or there's a whole bunch. You can make a species that is optically active, in fact, strongly optically active, and you can retain some of that electrochemical activity of your ruthenium system, so then you can play with this spectroelectrochemical light switch going from off to on fingerprints. Well, we started off with ruthenium and we wanted to model a Rutris-Bibi system simply because there's a ton of literature out there, really great benchmarks to compare against, really a great demonstration system initially when you think about it. The challenge is that ruthenium is, according to some very enjoyable articles from the 50s and 60s, a truculent chemical species. It's poorly behaved. In fact, getting it to combine with your different sensitizing ligands is incredibly oxidation state dependent. So for example, if we compare ruthenium to iron here, and we look at how iron will play around with something like acetate or acetic acid. If we look at iron 2, we see that iron 2 is really willing to get in there and form a whole bunch of different chemical complexes. But if we look at something like iron 3, we see that it really wants to stick with that bipyridine species. So there's differences in terms of how well you can get species to play with your complexing ligand based on what oxidation state it's in. So we started off with that. We wanted to build a sensor that would pull in your ruthenium, force it electrochemically into an oxidation state that is more willing to form sensitizing ligand or complexes with your sensitizing ligand. And then we could further use our sensor to switch that optically active species between its off form, so oxidized, and its on form, reduced. And to dig into that, we did a lot of electrochemistry exploring the system, looking at our blank system, where of course there's no electrochemical activity, looking at our ruthenium starting material once we get it in there. And of course, we see a lot of messy activity. Again, ruthenium is truculent. There's a lot of stuff going on there. But if we add in that sensitizing ligand and we reduce it for an extended period of time, forcing all of that ruthenium into the 2+ oxidation state that will combine with your sensitizing ligand, we can then electrochemically characterize the system. We see some new behavior grow in. And in fact, if we break down that behavior and compare to standards, we actually see that we're getting a lot of indication that we're generating that target optically active species. Now, I jumped through this data very quickly, and so if there's questions or people want more breakdown, we very much can. Just as a quick overview, we're looking at cyclic voltammograms in this particular plot, where we're looking at the output of a current as we scan applied potential. And in this system, we're looking for different couples. Primarily, we're trying to find this couple highlighted by the light blue couple right here, which is the ruthenium tris-Bibi couple. And we can see that in our system with our ruthenium chloride starting material, our sensitizing ligand, and after applying a reducing period, we get that couple to start growing in. Now, this is the electrochemistry part of it, but ultimately we're really after that optical sensor. We need that light output that can tell us, is our ruthenium here? And so here is a demonstration of how this sensor would work. So you can actually see your optical output out here. We're looking at your fluorescence signature as a function of time while we're running this sensor system. And to kind of break this down a little bit easier, we've got a 2-dimensional plot of that same data right below. And this is a double axis plot where we're looking at the intensity of our emission fingerprint while also looking at the potential that we applied to our sensor environment. And in this system, we started off with just our blank. So nothing but our buffer solution in there, no starting material, no ruthenium. And there was ruthenium in there. We applied this modulating potential, so going between fully reducing and fully oxidizing the ruthenium present in there. And what we saw was there was no change in our optical output. You can see the same up here. We then added that sensitizing ligand, the BIPI in this case. We modulated applied potential for an extended period of time. And again, we saw no change in that optical output, both here and again, you can see that up here. It wasn't until we added our ruthenium, excuse me, everyone, I got a bit ahead of myself, blank, free ligand, then we add ruthenium. It wasn't until we add the ruthenium in the presence of the sensitizing ligand and we apply a reducing potential that we start to see the ingrowth of this optically active species. Of course, as we switch to an oxidizing potential, pushing it to the ruthenium-3 state that's not optically active, we see that signal drop. And essentially we can keep playing with that, growing that signal as we generate more of our optically active compound, turning it off as we oxidize and so on. So ultimately we're seeing the sensor can generate our optically active species. And over here, we see that we can build calibration curves that actually let us quantify our ruthenium in our original sample based off of this sensor approach. We actually tried this with a couple of different sensitizing ligands, phenanthroline and bipyridine, you can see listed here. But ultimately, this is a very powerful approach that we can take into a lot of areas. Now, spectroelectrochemistry is also something that we can utilize beyond just sensor development, quantifying your target. It's also something that we can utilize to characterize fundamental aspects of a chemical system. And so here we're sneaking back into the molten salt data. This is some work that our team did previously looking at things like europium, lanthanides in molten salts. And we did a lot of work here characterizing things like diffusion coefficients, redox behavior, dependencies on temperature and salt composition. That we gained a lot of insight into how these systems behave. And ultimately what we're working towards is taking a lot of this lanthanide data, we walked through this quantification stuff here, and combining both this fundamental characterization with this quantification approach so we can start taking it and applying it to other systems that are less well understood in the literature, so actinides. Uranium is a big one that we're looking to characterize now. You can see some initial data, optical data, that's visible absorbance of uranium right here as we switch between different uranium oxidation states. Ultimately aiming to answer things like, again, diffusion coefficients, dependencies on salt composition in terms of its chemical behavior, and ultimately how we can quantify uranium in the presence of things like corrosion products or other species you'd anticipate within various molten salt environments. And of course, we're trying to extend into a very fun area, plutonium. Right here, you can see some of our initial electrochemical data from our characterizations of plutonium. So just a lot of work in the development in this area. Now with that, I might be running a little ahead of schedule, so we can take a moment here just to dig into conclusions. Again, online monitoring is an incredibly valuable tool to help us understand chemical processes or processes in general. If we utilize tools based on optical spectroscopy, we can get a lot of that chemical behavior insight or ultimately build tools that let us control or optimize chemical processes. And our team at PNNL is busily working on that, developing the technology, as well as training the next generation, which I want to highlight and show you the pictures of some of our team members here. And again, just pull up some acknowledgements for our funding sources, but again, our team members. And I really want to bring everyone's attention to this list of students and visiting faculty. This is a very short list. This is only from the last year or two. For example, we've got folks like Nicole here, who's actually joining our team through the ETI program. She's from CSM. And with that, talking about students, my team is not alone in the passion for bringing in students. There are a lot of teams out there that are looking to bring in interns of undergraduate or graduate level. There's a lot of different mechanisms for bringing students in, and you can see several of the acronyms here. I'd recommend just Googling that with PNNL and see what you can pull up, or you can go to this very convenient website that breaks down a lot of that information, or if you have questions, please feel free to reach out to me. And with that, I'll go ahead and thank all of you for your time.
Well, thank you so much. That was great. I don't do a lot of chemistry in my day-to-day life, but I think that I was able to sort of be reminded of how important, how fascinating a lot of it is, and really sort of gets me thinking about some of the opportunities if we can do this online monitoring well. We do have a couple of questions in the chat. First one was sort of about the PCA, back on slide 20, and sort of understanding how those principal components come about. I mean, you show in this example 4 specific spectrum. How do you determine, how does the loading, I mean, a question sort of about the math and the model that you acknowledge you don't have time to go into all those details, but how do we decide which of those are important and which aren't and things like that?
You're right. We probably don't have time to go through the math, but I do have some very exciting slides that I've been dreaming about going through someday when somebody's willing to sit through the math. But ultimately, I used chemometric modeling as a very general term in this talk, just to back up and make sure we're setting the stage to answer this question accurately here. Chemometric modeling includes a whole bunch of different mathematical approaches you can take. There's things like classical least squares, partial least squares, principal component regression like we've listed here, all the way out to things like artificial neural networks and so on. So there's a lot of different mathematical approaches, and basically all of those are geared towards digging into those details from your data that you're most interested in. So I think, if I'm understanding correctly, the question is, how does this chemometric modeling math even get into this data and start pulling out things like principal components or the information you're after? And the answer is, it, again, depends on what you're trying to go after. There's a lot of matrix math. There's a lot of ways to invert or optimize your data sets to get what you need. It's a tough question to answer without digging into the math on different modeling approaches and ultimately what they're after. I think what's probably the most valuable thing to say here is that our team does things like look at everything from, again, principal component regression to partial least squares to multiplicative curve resolution to artificial neural networks, are a big dream for at least a couple of my students, that will help us dig into different data sets differently. That plutonium data I showed you there, the model that pulled out those principal components was actually a multiplicative curve resolution model. Its mathematics are optimized to pull out those, fingerprints of those different chemical species. Whereas if we built a model for quantifying plutonium, we'd probably use something more like a partial least squares model, or maybe even something that's a little bit more advanced than that, simply because its mathematics are optimized to pull out, general quantification. It just looks at the data differently. I don't know if I'm getting at the answer you need here.
Yeah, I think you mostly answered my question. Thanks.
All right. And then another question about how robust the chemometric analysis is against the presence of impurities. So can you detect contaminants, and can you estimate the concentration of those contaminants with these methods and so on?
So also a really good question. The robustness of your model is entirely dependent on how well you build it. So we optimize our models for different things, and I'm a little bit bummed out I don't have a certain data set on here, but for example, let's go back to that CoDCon data, I think down here. So I just want to point out that with the CoDCon data, if we zoom in on any of these, let's look at some of these, for example. These are just some of our product streams here. And what you can see here in some of these are right here, for example, you've got uranium-6 in there, you've got some plutonium-4 in there. Usually we have some plutonium-6. It's a little bit tough to see in that spectra. So these models can be built to be very robust to a variety of optical fingerprints and interferences. And it really comes down to how flexibly you build your models. It's all about your training set. That's kind of the secret sauce that a lot of people don't talk about, is how you design a training set that will essentially let your machine learning system understand all of the challenges it can face and focus on what it really needs to focus on. So the CoDCon one was a good example of getting at some of these very complex processes, but we've also done demonstrations where we irradiated some of our probe materials or our probe windows. And I don't know if you're very familiar with what happens when you irradiate glass or fused silica or sapphire, but essentially if you irradiate what is a standard window material for optical approaches, you'll get a lot of a background grow in. Your window darkens essentially, and it can look sometimes like a neutral density filter, sometimes it can have some fingerprint to it, but something like that can just throw a non-robust model for an absolute loop because your baseline has gone totally out of whack. So we do things like take our data sets and we'll do things like normalize or put in appropriate baseline modification steps so that our systems, our models can handle even that changing baseline as you irradiate your probe and still output a meaningful quantification of your target. So it depends. There are folks who get very excited about their models and they'll do something like optimize their model just for a training set. Usually what that means is they'll do something like put just a ton of principal components in their model. And then that model is beautiful for their training set. But because it's so prescribed to that singular training set, anytime you throw something new or different at it, it's just unprepared. There's too many principal components that it's trying to work towards, and it can't deal with more complex data, more interferences or baseline impacts. Whereas we work very hard to make sure that our models are stripped down to the absolute minimum needed to robustly characterize those species that we're after, so that when something new or exciting comes in, like let's say your vessel starts corroding and iron starts creeping in and messing with your baseline, it can say, not important, I'll keep focusing on the plutonium. Again, that's a very broad answer to your question. I've got a ton of papers on that that go into a lot more detail. If you're interested, please reach out, I can get those to you.
All right. Cody has a question. Cody, you just want to unmute and ask it rather than me trying to read it?
Yeah, I could do that. So I see a big challenge with using optical, online monitoring, at least in the case of molten salts, is, since they're so corrosive and aggressive, the optically transparent material just really isn't there right now. I mean, has there been any work on what kind of window material might be appropriate for a long-term monitoring system?
Yeah, and that's a really good question. That is a big challenge as we try to move into something like a molten salt system where you've got that very corrosive system, very high temperatures, a lot of challenges that really probes or window materials can have difficulty with. So there's actually a lot of really good work out there covered in the literature for looking at different window materials that can go into molten salt systems. We tend to fall back on very hard things. Actually, I should say there's a little bit of a cheater's note here. The window material you can use is entirely dependent on the molten salt system you're looking at. So for example, if you're looking at something like a chloride-based melt, you can actually get away with a quartz window for an extended period of time. That chloride will eat up that quartz, but at a slow enough rate that your probe can really hang in there for quite a while. However, if you start looking at a fluoride melt, that's a different system. Quartz is not going to cut it. So you have to start looking at other window materials out there. And there's a lot of other window materials out on the market that are commercially available that work. And then there are a lot of more experimental materials out there that if you go and ask really nicely to the right people, they'll send you a piece and you can try to do a corrosion study on it. So yeah, there's a lot of work happening in that area to make sure that we can get these probes into these systems. We've had some pretty good luck with different window materials that we've looked at so far.
So I had a question, I think on slide 38, you were talking about with the ligand and the spectroelectrochemistry, is that the right word? There we go. So the kinetics here seem to sort of affect the time resolution, if those are the right words anyway. So it looks like it's sort of minutes for these species to sort of build in and decay away. Is that sort of fundamental to this, or are there ways to accelerate that so you can get, because that would suggest your ability to measure this is, within the resolution of that time frame.
No, and that's another really good question. This was actually the question you ask right there gets to the crux of what was heartbreaking about this project. Ruthenium is, again, it's truculent. It's very poorly behaved, and its kinetics are extremely slow. So in this system, you're right, it took us an extended period of time to force that ruthenium to start complexing with our sensitizing ligand. And then, you know, we could play around with it electrochemically, and it was relatively stable, but again, it just took forever. In fact, if you focus on this plot over here, my little zoom window is blocking me a little bit here, so I'll try to scoot that over and see if I can point out some things here. We actually ran a couple of different runs on this. We ran very limited time frame runs where we only converted a portion of the ruthenium to the optically active species. And essentially what you can get is the kinetics are consistent enough that the ingrowth of your optically active species is proportional to the amount of time you've spent building it up. That's what we fell back on here. It's not as sensitive as you would hope, and it's a little bit more, it's less elegant. However, we did do runs where we had to reduce those samples for greater than 24 hours so that we could convert the entirety of our ruthenium over to our target analyte and then quantify it. So yes, the kinetics were very challenging for ruthenium. Ruthenium is a really good example of one of those worst case scenarios in terms of metal species that you might be going after, let's say in something like groundwater or waste, where it's not already in some nice stable nitrate complex, but it's messing around in some less stable chloride complex. And really shows that we can take these probes or these sensor approaches into more painful environments. Ruthenium, again, being extremely painful. If you want to work with something that's really nice, iron. Iron is great.
And I guess my follow-up, I don't see, are there any other questions before I consume the last question? All right. So my follow-up is, and I think you alluded to this, but there's a lot of interest in these kind of things for safeguards applications, particularly when you look at molten salt reactors. So, you know, how you've shown methods that are good for identifying individual species, individual elements. If you wanted to try and get a more complete picture of what an online monitoring of maybe half a dozen or a dozen different elements and their speciation and things like that, is that something that you can sort of imagine, or are we still pretty far away from figuring out how that would all fit together?
No, that's definitely something we can imagine. And I think you reminded me of a part of one of the previous questions that I missed, which was, you know, quantifying a wide array, including interfering analytes that are not necessarily of interest. Ultimately, the number of analytes that you can go after and quantify in a chemical system are limited by a couple of things. Are they optically active? Are they in a concentration range that you can pick up? And do you have the processing power to run the models for all of these different targets that you have? So we have run online monitoring demonstrations where we followed, let's say, Hanford tank waste. I don't know if you're familiar with that. That's, you know, cleanup site. Hanford tank waste has just everything under the sun shoved in it. And so we've actually looked at Hanford waste tank samples where we are quantifying 9+ analytes simultaneously in there, even in the presence of even more interfering analytes that are there, but we're not necessarily interested in quantifying. You know, they're just the junk that's in the way as opposed to the junk we need to care about. So yes, we are very much there in terms of processing power. Now it's a matter of building the probes, getting them into systems, and optimizing or designing the models to go after those different targets of interest.
Great. Well, thanks so much. Well, I think we're out of time. Fascinating talk. Thank you so much. Thanks for joining us. Wish we could give you a proper round of applause, but you'll have to just imagine it instead. And with that, we'll end the recording and close the session. So thanks so much.
Thank you.
Thank you.